have to get the all-important chat monitor up. Okay, I think I'm going to make some warm tea, and then we're going to proceed. So, yesterday I was working on some stuff having to do with checking arithmetic operations for overflow. And got somewhat far. And then I realized, oh, oops, the way I'm doing this is not actually good. This is something that happens a lot in programming, no big. But I think my correct thing to do, I think everything I've done is usable. And I just want to go back and modify. So wait, I left the R here. Okay, that's fine. I didn't mean to do that. Why are devices popping in and out? What is going on? Oh, that's on the Razer laptop over there that has never worked correctly. I'm not surprised at all. Okay. So we're going to put this back. 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 And we're just going to make it compile. And then we're going to have to make it run. As always. As always. Okay, so these just make these instructions. Oh, we gotta do this one. That's important. Okay, my tea water is ready. That's good news. Okay. So, all the places that call this are now not passing that argument. However, only 2 places call it. So that's one thing. However, there's another thing, which is that what we're doing here is we're going to make this an either-or situation now. We used to emit both of these instructions, and this one would just check, and this one would write the result. And now I'm like, It probably is better to make this one write the result for multiple reasons. So we're doing that. Okay, so So we do this. Now, let's make sure that compiles. It doesn't. Oh, it's C++. What am I thinking? I'm not allowed to do this. You can't just change things in C++ without changing them in 5 places. Alright, so we've got more calls to this. Okay, and I made copy pasta errors in these locations, which makes me nervous. It makes me nervous about this whole way that this is being done. There's like a giant union of all these things, and like you can just pick the wrong one. It's not that great, but we're going to see if it actually causes a problem. All right. So this is wrong. This is wrong. That's wrong. Okay. So now if we run this, it should be a disaster at some point. Although, let's just try running Sokoban. Yeah. Yeah, so the reason is that now during compile time execution, we said we would write the result of math operators, and we're not actually doing it. So none of our math operators are working, so we can't even, compile the program, which is no surprise to anybody. Now, here, let's assert that we don't get here now. Okay, so here is a bunch of code that I fucking did. And what is it called? Print. Run math bin up. Okay. So the compile time execution code for this stuff is very lazy, and that's fine. We just lean on C++ to do the maths and stuff. The problem with that, because we effectively want the same result for truncated operations and things. This one is supposed to check for overflow in maybe a way that's more explicit, so it blows out into a bunch more explicitly written cases and stuff, it just is what it is. Like, I tried to avoid this kind of thing early on in compiler writing, but it just, literally, you have to do it. Like, if you've got some operation and it runs unsigned and unsigned things of 4 different sizes, you need 8 different cases per every flavor of the operation. That's just what it is. Okay, now, look at that backslash. So basically, we just want to do this. For all of these cases. Except, of course, this is wrong. And subscript, this is the scary part, has to be every time. So I'm going to pasta this. So we have plus and minus and times for signed and unsigned. And We're not even doing divide. You got to check for overflow on divide because there's exactly one case when you overflow. Okay. C++ macros are miserable. This is true. Although macros are kind of hard, to be honest, because as ugly and horrible as the C model of macros is, there are benefits to it. So like in this language, because we're more structured about macros, there's just places you can't use macros. So if I can figure out a solution to that, that'll be nice, but it's not that easy. Okay, I'm already doing the wrong thing. I hope somebody caught this. I thought the pattern was going to be the same thing going down. It's not. It's size going down every time. Do we think the tea's ready yet? I don't think so. So here's the thing. The way this is being written, this in my brain is closer to these, and that's going to lead to a mistake. Now, the order in which we do this versus this doesn't actually matter. So I'm going to do that. We're going to swap Rooney this. Now these, okay, by the fucking way. These are all wrong. Okay. Now it's even less readable. Great. Okay, but we're going to swap Rooney these anyway. Now they look closer to me. We don't have an R there. That's going to give us a compile error. I'm not going to worry about it. I'm just going to go. That's what I get for pasting all these in the wrong place. Should have pasted them in the right place to begin with. Times. See what's become of me. This is, you know, when people say ChatGPT is so good at writing code, this is what they mean. Extremely repetitive dreck that you would rather not have exist at all. It's great at that, kind of, except it's not because it doesn't usually work. But, you know, like I've had people email me and say, oh my God, I've used ChatGPT. It's so great. And I'm just like, my opinion of that person goes down because it's like, now I know what you think programming is. I mean, I don't want to be a dick about it, but that's basically exactly the mental response that I have. It's like, oh, that's what you do all day. It's a different thing. You do this all day. Except this is actually more interesting than like web glue code. Okay, I think we're done. I'm going to get my tea. And then we're going to go over and check all of these manually, because this is exactly where you always make a mistake, and then spend 2 hours debugging. Tried using it for MATLAB and it just endlessly invented methods. I know, but didn't it save you so much time in inventing methods? Guys, I have an emergency. Someone stayed over at my apartment the past few days while I was gone. And now I can't find the tea strainer. Fortunately, I had a backup. Also, this person bought sesame milk, and there is now sesame milk in my refrigerator. I like sesame seeds, but I don't. Let's go read the instructions on sesame, or the ingredients. Okay. The carton makes it look like it's for girls. I don't have a camera for you. All right. Okay, first of all, guess what the first ingredient of sesame milk is? Sesame milk. It literally says the first ingredient is sesame milk with parentheses of what that means, which is water, sesame protein, and pea protein. And then cane sugar, okay? And now ingredient number 3, because when they do the parentheses like that, because it's like hierarchical, that's what's in sesame milk. I can't tell how much sesame protein there is compared to things outside the parentheses. See, it's a dirty trick that they play. So cane sugar, and then guess what? Guess what comes right after sugar? High oleic sunflower oil. Seed oils. Calcium phosphate, natural flavors, toasted sesame oil, sea salt, sunflower lecithin, gellan gum, vitamin D2, contains sesame. Yeah, this stuff's disgusting. It's salad dressing. Yes, it is salad dressing. But it's not even good salad dressing. Because a good salad dressing would have like olive oil or, vinegar or something. It wouldn't have seed oil, aka industrial lubricant. You want to know why all Americans are sick and their bodies don't respond correctly to food inputs? That's a clue. Can I give you advice on where to start graphics programming? Ask ChatGPT. Why are you asking me that? ChatGPT knows. Everybody is so hyped about how ChatGPT knows. Okay. Now that we have our T, we are ready to actually, okay, U64, U64, U64. Okay, this is what we're checking. The assignment, great. U32, U32, U16, U16, U8, U8. I'm going to literally click on every one. S64, S64, S32, S32, S16, S16, S8, S8. Yo, S8, that is 64, 32, U16, U8. S64, S32, S16, S8. U64, U32, U16, U8. S64, S32, S16, S8. Oh my God. It looks like I didn't mess it up. Okay, now we're still not going to compile because, like I said, a couple of these don't have an R variable. Like I said. So, but that's fine. Make sure we're in the right place. This is for plus, yeah. Okay, so there's at least one more of those, probably three more. Oh, several more. So this doesn't have an R. B minus A. No, A minus B. A minus B. Here we're just being sloppy. C++ has very sloppy rules about, implicit casting and stuff that lead to all kinds of bugs. And that's why we're adding these features. Well, our casting rules are already a lot better than C++'s, but we're also adding these rules to help with it. All right. We're getting possible loss of data. Yeah, we could put the casts in. Let's make it work first. Hold on. This is not going to be plus. This is minus. Yeah, I almost goofed real bad. Wait. This is wrong. Because I copy-pasted it from plus and didn't think enough. This is A minus B. Okay. And then these are right. These are all minus. See, like these are the easy cases where our word size was big enough, and here we had to do a different thing. All right. And then here, I'm just going to do that. Some of these are going to be wrong, and it's going to be a horrible debugging slog. Hopefully not. Let's not bring that into reality. Okay. Yep, it crashes, but not the same way. Here, nothing was working at all. Now, I mean, we're in the allocator, which is a bummer. So I could just go back over the code because there were several mistakes there. So chances are we would find another mistake if we just go look at it, especially those more complex cases. But to give us a little variety, let's at least look at this. Okay, this is pointer math. Which I wonder if we're doing the addition. You know what? Let's take out pointer math for a bit because it doesn't actually help you much to bound check pointer math anyway. So this is our pointer math section, right? Yeah, maybe emit pointer math. So we're just going to do this for now because, like I said, this doesn't really help us. And that way I only have to think about the simpler thing. Hey, our Sokoban game compiled. It's doing a lot of compile time execution. Well, I don't know. The meta program is, but it doesn't have these bounce checks turned on. I kind of want to just default them to on and compile everything because A, that'll test the code, and B, it'll tell us. So one of the things that may come up while we're doing all this is, oh, in the modules and stuff, there's overflows that are happening either because they're a bug or because they're not a bug, but we're going to need to mark them as intentional. So for example, you know, if you have a hash function, it's overflowing all the time, but that's intentional, right? So yeah, let's go to here. Wait, we have it defaulting to non-fatal. That's a weird setting. Okay, I'm gonna no check in there. Okay, we're defaulting them. And no check in there, and then gonna no check in here. So we're just gonna leave them on all the time. See what happens. It's gonna generate slower code. Oh, you know what? Stuff ain't gonna run. Watch this. Wait, how is this running? How is this even running? Someone explain. Hmm. 10:26 a.m. according to who? I guess this shell was started on East Coast time. I don't know. I don't know why that worked, because yeah, this is the worst kind of it just works. Let's just make sure this is happening. So if I compile this, okay. So this is all correct. I just want to make sure it's the right compiler here. Yeah, so this test case was made to, to run F at compile time. F intentionally generates an overflow because U16 can't hold 80,000, right? So that report is working. By default, I didn't have to pass anything to turn that on. But let me, so now if I do this at runtime instead, yeah, okay. So like I said, things shouldn't run, and this doesn't run. But like, what? How did the game run? Oh, you know what it is? I bet in our games metaprogram. I mean, we override this, but non-fatal should still do the check. Maybe it doesn't for some reason. I don't know. Okay, this, I expect this, because the problem is our new instruction doesn't do the old instruction. So, this is totally expected, but I don't know why the game ran. That's creeping me out. Did I run the right executable? Look at all this stuff it's doing. It's loading shaders. I'm on the elevators. Well, what do we think? What do we think Chunky's deal is? I mean, I can just work with this for a bit and not worry about it, because what's going to happen is all these tests are going to fail horribly, right? Let's just, whoops. Well, first I have to put in the right name. So these are just going to just vomit. Yeah. Like we don't even, it's all messed up. This is because, again, all our math operations don't work. Now, what I could do is here, we're just going to comment this out. And we're going to do this for now. Now we need to do that in LLVM as well. This is never admitted, so we don't need to worry about that one. Okay. Now maybe things will run. Okay, there we go. Wait, yeah. So we're still doing 80,000. That wraps, right? We get 14464 plus 65536 is 80,000, right? This is the right answer, mod 65536. And we're not doing the check, obviously, because we're not emitting it in the machine code. But when we turn this back on at compile time, we do the check. Okay, that's great. So the status of this is we are emitting the instructions. They seem to be doing the right thing all the time or almost all the time at compile time. We're about to run through all the tests to see if we can catch any more problems. And runtime, they just default to the non-checked operations, which is fine because then the next step will be adding checks to the non-checked operations when need be. But probably what I'm going to do is take the W for this. Oh, no, we can't take no W's while that's happening. So we still have a problem. Boy, look at all these. Hopefully it's the same problem for all of them. This is why we run z-tests. This is why we run z-tests. Arithmetic overflow. We tried to compute. Oh, okay. Well, these are legit. So Knuth hash probably isn't. I thought I went through there. Knuth hash, okay, does not say no AOC on it. Ta-da! Okay. Other ones. Knuth hash. Knuth hash. Knuth hash. Knuth hash. Knuth hash. La la la. All right. Easy clap. Let's run it again. When do you call a version a new version? It doesn't necessarily matter. Why do we have more fails? I thought they were all Knuth hash. What's going on? Let's run this one. Okay. I've seen this one before. This is a weird bug. Something is wrong here. Because, of course, 52 minus 0 isn't going to overflow in anything. But I think this is actually a float operation. And we should not be outputting this. I saw this the other day when I originally wrote this code. And I was like, I'll deal with it later. And I guess now is later. Let's just look at this, though. Mantissa bits minus 1 minus E. Let's do we get this when we go example here? No. So what? The problem with this module test is it doesn't tell me. Oh, wait, we're here. See, it's not happening, though. I wonder if it's a weird Heisenberg. Let's run. Nope. This is probably setting up the compile time environment a little different. Arithmetic overflow during compile time execution. Okay. We're just going to break in that error message because then we can inspect the types of the things and whatever. But I guess, okay, these are integer operations actually. So maybe our printing of the values is wrong. That's a possibility. Although E, so yeah, I don't know. I suspect maybe our printing of the values is wrong. Let's see. So we jumped up on the table and we shouted anarchy. Someone played a Beach Boys songs on the jukebox. I mean, versioning, like, yeah, like it's useful for people to know if something is the newest one or not. And it's useful for people to know if something is a specific one or not, right? Is this the specific version that I have, or is this the new? Those are the two questions you need to answer, okay? There's lots of ways of answering that. A monotonic integer that counts up is all you need for that, right? So, yeah. And then, there's, of course, other things that people try to communicate, like if it's a major version, maybe that means more is different or whatever, but that stuff doesn't matter as much. Okay. Okay, it's a bad sign. We've already got junk in our file, junk in our trunk. Yep, Control M. All right, we got to start it over because I will not tolerate being a line off. how updates are built up as this amazing thing in most programs. Well, I mean, it's a broken culture of software, right? Like nobody is able to view the fact that we have to update our software as a bad thing. Like, why wasn't it already good? Why do you have to keep fixing shit, right? Okay. So, it claims this is a 32-bit operation. We're doing A. What do you mean A and B are not defined? Oh. The fuck? Why is my debugger... If you ain't got no debugger... Is it because of fucking... It's because of this, isn't it? Fucking piece of shit debugger, dude. It's like they make it worse every time. So the bug is if you're on a function call in the last statement in a block, it scopes you past the end of the block. All right, so you can't see local variables of that block. Hey, look, I can see A and B now because I wrote int k equals 1, fuckers. Like, it wastes so much time, these stupid ass bugs. By the way, this used to work correctly. So early versions of Visual Studio also had this problem. Then they got a fucking clue and they fixed it and it worked well. And then Microsoft decided, oh, a manager will get a bonus if we rewrite Visual Studio in C# because that'll make everything better. And it has never been, ever since then, as good as it was before they rewrote it in C#, right? The final C++ version of Visual Studio was the best one. Although Sean Barrett doesn't agree, he still uses Visual C++ 6. Okay, so literally it is 52 and 0. So my check here must be wrong. R, 52. Okay, I'm missing a minus sign here. Somehow I flubbed this. So we have to go check, because there's multiple cases of this, we have to see if I did that more than once. See, there we have the minus. Minus, minus, minus. It's a 50 DKP minus. Minus, minus. So somehow I must have like fat fingered a delete at some point on that. All right. Hey. So that was fine. It was just our check for overflow was oopsied. Now they're trying to get Rust in the kernel somehow. Yeah, I mean, yeah, it's a long story. I'm not going to comment. Like, I like that Rust wants to try to solve actual problems. On the other hand, you know, they massively overblow what those problems are. And the problem is that's not the only thing. Like, software culture is super broken, right, across the board, and they inherit all that brokenness, right? So, hey, they're not going to have that many buffer overflows. It's like, great, neither are we. But meanwhile, you guys are inheriting all this brokenness that's leading to the most giant, most bloated, least functional software in history. And so you got to fix that, right? Okay, get memory hash. That has got to be get memory hash. Hey, look. No AOC. Okay, this looks like a crash trace, but it is not. This is us reporting you know, it's us reporting things. Okay, that's great. Yeah. It's about time to take the W. We got to run the tests. We should run them in release on LLVM as well. Let me get rid of our no check-ins. We're going to turn this off for a minute. I feel like we have at least one more. Maybe it was in Sokoban. All right, release compiler. And if this works, we will take the W. Yeah, the quasi-religious identity. Yeah, I mean, that's the being so sure about exactly what the problem is and that you are the solution to the problem is, you know, it's always a negative, right? Because the thing is, problems are actually nuanced. And problems in software are large and extensive, right? And claiming that you have 100% of the solution because you've identified something that's a legitimate problem. You have found something that does help with that problem, although there are trade-offs that maybe one should take seriously. It just, like, giving yourself license to feel righteous over that, it just incurs blindness to all these other problems, right? And those other problems are fatal. They're more fatal. Here's the thing. Buffer overflows are bad, and it's stupid to have them in your programs. But do you know how little we fucking care about buffer overflows actually? Like, okay, everybody freaks out. Everybody says, like, oh my God, software is so insecure because you can do these buffer override attacks and shit. You guys know, the experienced programmers in chat will know that it's trivial in C to neutralize the effect of like over 99% of those buffer overflows attacks. And nobody even gives enough of a shit to even do that. Like literally nobody cares. All right? And if you're wondering what I mean, okay, the thing that makes those attacks so dangerous, the biggest vulnerability is you override a buffer such that the end of the buffer stomps the return address, right? And you put the address of your code that you want the program to jump to, right? And it returns to that address, and then you take over the code. Okay, that's the number one buffer overflow attack. It's trivial to make that impossible. Trivial in C. And nobody gives a shit. Nobody even bothers to do it. I mean, by nobody, I don't mean literally nobody, but almost nobody. Right? All you do is you put in your compiler, and compilers all have an option for this, by the way. Clang and GCC have this option. You put in your compiler, hey man, I want there to be actually two different stacks. Let's have one stack for the secure data, such as the return address, right? And other compiler-controlled things that need to be unscathed by errant user input. And then we have another stack for all this shit. And then maybe if there's an overflow bug, it'll overflow the intended thing and it'll go into other data arenas. But those other data arenas are not critical to the control flow of the program. And so it is much, much harder to attack the program. Nobody does it. Nobody does it. So given that empirical evidence that nobody even fucking bothers, how are you so convinced that buffer overflows, like fixing buffer overflows is the panacea for the world? Because we already could have done, we've known how to do that for we've known how to do it forever, but let's look up when these options went in. I forget exactly what it's called. Secondary stack option. Stack protection. Say shadow stack is what they call it. I think. Okay. When, this is exactly the kind of question you can't ask from Google anymore. When did GCC add this? I don't know. We could ask ChatGPT, but it would just make up a year. It was a long time ago. Chromium fixes tens of memory bugs. Yeah. Look, what you're saying has nothing to do with what I'm saying. So, you would not hire me, I would not hire you. Yeah, I just, at this point, I just can't tolerate Hacker News dudes who have their claim to fame in software engineering is they wrote FizzBuzz 2.0 and they think they know everything. Is verse DOA? I don't know. So here's the thing. I haven't looked that much at verse. Like specifically. I did talk to Tim about it. I went on a hike with Tim in like 2021, and he was telling me about how it was going to be. And it didn't sound like my kind of programming language, but like it's pretty wacky, right? I fully support trying wacky things. I fully support it. Is it the kind of language that I want to use to do the kind of things that I want to do? Not really. No, it's not a systems language really at all. Although he might tell you that it is. I don't know. Let's look for this. Glendale Community College. Dude, does the dash mean something bad in Google? I don't know. It's impossible to find information anymore. Stake. Enable shadow stack built-in functions from control flow enforcement. Yeah. Anyway, the point being, I don't know. Somebody can search and try to figure out when this option was added. It was a long time ago, dude. Like I think I was talking to Tom Lord about this in the 90s. Okay. In the literal 1990s. So we've had this forever, and people don't even care enough to use it. It should be the default, actually, on C and C++ programs. And I don't know why it isn't, but it should be. You want to exclude all sites that have this keyword I see. Okay. You've not heard these ideas before. Well, see, this is what I'm saying, though, right? This is what I'm saying. And I don't exactly understand. I don't understand what happened here is what I'm saying, because this is obviously a good idea for C programs. Now, it does incur a small performance penalty, because what happens, because you have two stacks, right? Now, whenever you return from a function, you have to like manually pop the other stack as well. Okay. But that's like a couple of instructions per function call. And for many, many years, we've been in a regime where a couple extra instructions per function call is effectively free, because programs spend all their time waiting on data. And if you have a function that's so small that matters, it's probably inline these days anyway, because compilers are very aggressive about inlining. So, it doesn't, like, it's obviously should be the default. Like, this should be -no mstick to not do it. And yet nobody cares. And the fact that nobody cares makes it weird that everybody's acting like these kind of attacks are the worst thing in the world. I agree they're bad. I'm not saying these attacks aren't bad. I'm not saying these bugs aren't bad to have in your program. They are bad to have in your program. But the mystery to me is nobody cares. It's just like everybody on the web doesn't care that it takes 10 seconds to load their web page, and they claim it's actually as fast as possible. But you go to the web page and it obviously takes 10 seconds to load, right? It's like, okay, everybody gives lip service that these kind of bugs are bad, and yet the obvious mitigations are not performed. There should be hardware support for shadow stacks. I mean, that would be fine, but you kind of don't need it though, because it's a general purpose CPU, right? Like, you're fine. What a great flag name. Yeah, oh, I know. This is in the Unix tradition right here. Yeah, like, this is inexcusable to me. You're like, okay, you could learn another programming language and literally rewrite all software, or you could use this compiler flag. And it's like, nobody does. I mean, that's a little bit of an overstatement, because you would still, again, you would still have buffer overflow bugs in your program. This doesn't get rid of the buffer overflow bug, but what it does is it makes it dramatically less of a security risk, and it makes your program much harder to attack, and it makes it much less of a vulnerability, right? So yeah, exactly. It does not prevent overflows from happening. So what'll happen instead, because instead of like the return address, what would be next up on the stack would be, you know, other data from your own program, right? So then your program probably crashes or whatever. And you can, you know, it would be possible in some cases for some programs to figure out how to maliciously put data into other variables to get the program to do things that it didn't want to do. But this is tremendously harder than just stomping the return address, because you have to analyze and understand the individual program and blah, blah, blah. Like, the situation would get so much better if people just did this. Does the Linux kernel use it? I don't actually know what the kernel does. I'm not well educated on the Linux kernel. The thing about the kernel is it has other it has a whole other layer of permissions, such that, well, yeah, I don't know. I shouldn't say much about it, not knowing. Are buffer overflows at normal? I mean, here's the thing. In a C or C++ program, yes. So C and C++ are very error prone in terms of, you know, creating situations where you're going to accidentally overflow a buffer. So yeah, C and C++ programs tend to have a lot of these problems. Programs in other languages, even just that are one step away from C or C++, do not tend to have remotely as many of that kind of problem, because the abstractions are just different. So for example, in D or like Go, Go, you don't really do raw pointer stuff, but it's got the similar thing semantically where you're passing arrays around all the time. See, in C and C++, you pass like a pointer and then maybe a length that your program uses to know how much valid data is in the pointer, but the compiler doesn't know that those two things are associated, so the compiler can't really check automatically or anything, right? In many newer languages, including the one that we're working on now, if I will shut up, you don't really do that hardly ever, right? Instead, you pass arrays around, and arrays are bounded, and so your errors get caught during development. And that's very useful, right? So before you even talk about, making memory more safe in some fundamental way, the thing to realize is that most new languages are much better than C and C++ about that kind of a thing. to begin with, because just the patterns are different. Since Tiger Lake, Intel has support for hardware for shadow stacks. Okay. I have not looked into how that works. I mean, it's probably largely to do with exception handling, right? Because that's the other annoying thing, is like if an exception goes off, you know, what do you do, etc. Do we treat pointers like they're evil? No, we don't. Safe stack is from around 2014. Interesting. I'm surprised it took that long, because like I said, people were talking about that in the 90s. It was probably just more of a manual thing that you had to do. Mschustik. Canaries also exist. Yeah, I mean, canaries are good as well, but they serve a different function, right? A canary is to tell you, well, it depends. You could generate canaries that work in arbitrary ways, but the most common one, the most classic one, is to just tell you that you effed up while you're developing, right? Like Visual Studio had those going way back, and they were really useful. I didn't say Google and Microsoft don't know about the flags. I said nobody cares enough to use them and or make them work well. Imagine using Google or Microsoft as your example of high quality software engineering. Roller coaster. Okay. I should have, while we were talking, run the release compiler, because that's where we left off here. I'm going to run this in LLVM as well. If those both work, we will take a W. Like, that's how you know someone isn't really that experienced at programming, is they're like, how dare you suggest that Microsoft doesn't know what's good, right? How dare you suggest that Microsoft isn't the best programmers? I'm ordering some hot tea, but the waitress says no. We only have it iced. Progress on arithmetic overflow checks. Okay, so that appears to be pretty good. So the next step is going to be implementing this in the back end. Is there still k equals 1? Yeah, I tend to leave those in there because like I want to debug sometimes. It's stupid, but they're in there. Okay, I put a lot of tea in this time, so we're going to have to not forget. Now, in the back end holios, see, here's the thing. I could just do print math bin op followed by a jump. We're going to need the jump either way. It's going to need to be a jump if no overflow. All right, and it's probably OX81, but let's see, JNO instruction. JNO 81. Told you, OF81. I could have just typed OF81 and people would have been like, oh my God, how does he know? All right. So this thing that I was doing basically up here could be inside an if statement. We could be like, what's the variable called? I don't have a key to jump to the, okay. So I could do the regular bin op output and then check. See, the thing about on the CPU is you could easily tell if the operation overflowed, unlike on the in the C++ program. However, that is only true depending on how we do the operation. Okay? And I don't remember this. We're going to have to go look it up. If we're actually doing adds of the appropriate size, then, right, so we could, like, for example, if we're doing an 8-bit add on 8-bit values, we can check for overflow. However, what worries me is I think we're not doing that. I think, knowing me, what I did was we load sign extended from the 8-bit thing into 64 bits and just do the operation in 64 bits. And if we do that, I don't think overflow is going to help us. So that would mean we either need to do these operations at the correct sizes, or we need to do range checking like I did in the C++ program. And The problem with the range checking version is I think we're just outputting a lot more code all the time, right? Like asking if the overflow flag is set is very compact, whereas saying, is the result greater than or equal to this constant and less than or equal to that constant, like literally every time, is more code. And so I don't think we want to do that. Okay. Let's take a look at how this works. Oops, sorry. I meant for this to say this. I just didn't finish the thought. This is what I meant here. So we do this for either one, and then if it's this, we do this. Although honestly, there's no reason not to do this the right way if we do it this way. Because it's only like a one-line pasta here, here, here. Yeah, that would be better. And then we can actually do that correctly. Okay, so we have to look at print math, print math bin op. Okay. I'm getting worried about my tea. So we do mul s underscore and pass the size. Okay. Oh, that's for float. I was looking in the wrong place. Yes. Add sub imul. Let's look at imul. I wrote this a long time ago. I wrote this on stream. So let's look at 2-register math as well. This looks like it's actually doing the correct size operation. Except imul doesn't really. Imul is doing 8 all the time. We only care about addition, subtraction, and multiplication right now. So what the fuck? Wait, what? Okay, when we load the registers, we must be sign extending all the time. But in these cases, we're doing the right side. Let's verify, right? That's what they always said during Gamergate, trust but verify, or whatever. Okay, so let's make a new thing. X, U8, Y, U8. Z is X times Y. W, we're going to do plus first and then times, and then so we're just going to do that. Okay, and we're going to step into that. Okay. Windows disassembly. Okay, we're storing 0 on the stack for these. I actually don't know why we're doing that. Let me get my tea. Okay. So we're going to skip this. Okay, so here we are doing a 1 byte add. So that's fine. We are, however, doing an 8 byte multiply in each case. So that's bad because we can't overflow check that. Is it actually slower? Are smaller IMLs faster? I doubt it, right? But we're going to have to figure that out. And that'll be a big enough change that we're going to want to take the W for that. I think what we'll do is we'll make a function that tests IML at different sizes. All right, here's what we're going to do. We're going to say do the mul T is a type, and that's it. We're going to A is 5. We're going to do something that doesn't even overflow with S8, and that's also unsigned, so we can do signed and unsigned types. I swear we wrote this before on stream. But anyway, B is going to be 37, right? C is A times B. Assert C is equal to 185, right? Okay. Cool. Now, do the mul U8 So we're just going to check that this comes out right for all the sizes. Right now it will, because we're doing the same size multiply, but then when we modify the code to do different size multiplies, we want to make sure we don't screw it up. All right? Let's print T. All right. Import basic. Cool. Dude. What? How are we not getting the right answer? Let's put the assert after. Minus 71. Oh, wait, what? Oh, because, yeah, of course. This is too big. 17 times 5. Okay. Yes, 185 is, I was like, it couldn't, this is how long I've been programming on massive hardware. I'm like, wait, 127 is really small. That couldn't be the limit. Yes, of course that's the limit. But in my brain for a second, I was like, what? Do intrinsics work? We have an assembly system that is functionally similar to intrinsics but different. .127 is the highest number. Okay, so this is our test, and we will be able to step through that later also and verify that the assembly instructions are good. How many callers do we have? We sort of have this choice. Do we make a new IML, or do we just replace the old one and do the size? We have bin-op times calls IML. This thing calls for stack trace node, and that's it. I think we just do it. Okay, so IML instruction. Wow, remember the days when we were doing this for the whole backend? Oh, we're all familiar with this website. I wish you would change the fucking background color on this website. Oh my God. Okay. So now we had this 2-register math, and I didn't use it for IML, and I don't. So this, we probably can use this, right? So it puts the 16-bit prefix, it puts rex w, math mode, which is this. Let's see. If size is 1, we subtract 1. Math add. Let's see. F7. F7. Oh, those are the implicit. We don't want to use those. Fuck that. So this is putting this first, and then the mod RM. Dude, I hate x64. All right. We just want these ones. There is no 8-bit IML. Except for fucking this. When they went to do the later instructions, they're like, nobody's ever going to want an 8-bit IML. Of course, we do, because we want to bounds check that shit. But we could just emit a more disgusting code in that case. Who is my favorite rapper? Afro Man is a good guess, but the correct answer is MC Hawking. Okay. I mean, this is welcome to the world of being frustrated. I don't know what the hell all this means. Again, I have to figure all this out again, dude. All right. So it looks like 2-register math doesn't really work for this, I don't think. But that's fine. We're doing OF-AF here, right? So I'm going to do this. Okay. And then we're going to do the 16-bit prefix. Here's what we're going to do. We're not going to worry about the 8-bit add multiplies yet. We're just going to do the other sizes. If size is equal to 1, we're going to fall back to the old thing. Okay, we're going to do OF, AF, and then /R, which is kind of this, right? Okay. So we only want to write the recs if the size is 2. No, if the size is 8. Oh no, that's It's been a long time since I did this. Oh, I closed the compiler. Okay. All right. Maybe that works. Now let's step through. Okay, do them all. Disassembly. You know what? Let's no. All right. IML AX. Okay, so that's a 16-bit multiply. Okay. We're going to step into the 32-bit one. EAX, okay. So, assuming, well, this appears to work for all these sizes. So we got to do 8-bit. And for 8-bit, like hardly any programs are going to do 8-bit muls. So if our range check is less efficient, I think that's fine. Let's just make it sizes 2. Right? And then I think, oh, I don't know why I commented this out, because these, we want to at least make sure those work. It's just going to be range checking them is going to be more annoying. Okay, so now we'll do tests on everything. And then we'll take that W. We're going to tell people about this on the x64 backend. Integer multiplies now are correctly sized according to the operands. We used to always do 8-byte multiplies. It's a small thing that hardly anyone's going to care about, but it's in the change log. Can you just do a 16-bit mul and see if the high 8 bits are 0? Yes. It's actually Hacker's Delight says, so of course, because the compile time execution is in C++, we had to do all this. I did that one first because it was going to be, actually it's the second most annoying. LLVM is the most annoying, right? But that's what we do. You actually, that's for unsigned, right? And then for signed multiply, okay, where are we? Minus, like, look at all this disgusting code, right? But basically, for 64-bit, we have to do that. Wait, that's unsigned. Okay, signed multiply is the most complicated one. Basically, if the top is negative, right, that means your whole number is negative. So it had better be all ones. This didn't come from Hacker's Delight. This was me just sitting down going, what's the thing? So if it's negative, it has to be -1, right? Otherwise, it has to be 0. Yeah, it's pretty simple. It's just outputting that is annoying, right? Because it's like, I want to do it branch free. I don't know. Wow, there's people here with faces. Why do all these people have faces? I thought faces weren't allowed on Twitch now. There's all these rules that they have. All right, so this compiled and ran. So this is good news. If we can run the game with our new muls, the game surely does a lot of integer muls. Sukoban. Sometimes I spend time thinking about what this game should be called. I never thought of Sukoban. 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 That would sell very well in Russia. All right, so, you know, the game's running. It's pretty good. So Sukoban would be, it would be like a cross between this game and I Want to Be the Guy, where like you see the solution to the puzzle and you start doing it, and then a stone falls into place, making it impossible to do what you were trying to do. Okay. Because ruble does not feel good. Well, I don't know about that. All right. IML is now at sizes 248 in the x64 backend. All right. So, oh, I put a no check in. Why? Why did I do that? Oh, because that seemed like a stupid hack, but it's what we're doing. Okay. So I think the next step is to do the range checking, but only do it for the sizes that we have, right? And then we'll add in the 8-bit. But also, okay, so what does range checking look like? It looks like do the multiply. If we overflowed, call our error report function, which is this. We've literally never called this yet, but this does some stuff. This expects certain parameters. We've never even emitted code to call this function. So maybe what I should do, the first step could be just claim that every single multiply overflows and calls this function, right? And then we'll know that that works. And then what we do is we say, okay, do the multiply. And then if the multiply is fine, jump around this call, right? That's how we do it. Okay, so here's, so we're going to delete all this. I was going to do this by blowing out all the cases just like the C++ code, but we're not going to do that. So here we go. We're doing, okay. So before we put this in, oh, dude. I was actually putting the jump in all the time, so we had a jump to nothing there. That's great. At least the jump didn't kill the program. That's useful information. Okay, so array bounds check fail. Here we go. Add entry point patch. Oh God, code gen panicker. Okay. These are so much fucking code. I want to figure out how to make this smaller. But God damn, dude. So these are like callbacks that we pass to a thing. I don't know. Let's try filling it out. Okay, code gen panic arithmetic overflow. If we're passing arguments, what is this? Array index. Array, okay, so yeah, these are the arguments that we put in. These are the lotion that we put in the basket. One USD to 89 rubles. Well, what is it usually? What is the exchange rate historically? $89.50. Okay, 5 years. I mean, okay, pre-COVID it was 60. That's a lot, really. Yeah. Yeah. Gee, it went up in 2014. I wonder why. I wonder what happened in 2014. That's kind of crazy, though. I didn't think that the exchange rate had that much of a thing. Okay. Okay. So the waitress said, no, we only have it iced. All right, so we need to make some registers for the arguments. Let's go, because we put these things here. Like, this is questionable how all this is done, but I'm not sure that I know a better thing that would obviously be cleaner. So I'm not gonna do it yet. These should all be value number. Like, I just don't want to use int in cases like this anymore. Okay. We're going to need, let's check runtime support. So these should correspond to all the arguments, right? So cast bounds check fail. We have a pre-value, pre-flags. Oh, wait. These were actually fucking ints. Yeah. This is why. All right. Pre-flags, post value, post flags, fatal, and then line number and file name. I don't know where those come from, but we're doing something with that. Okay. So arithmetic overflow has arguments. Cogen panic overflow left value. I don't like using the word register. This is really old, so I'm going to say value, right? And then right value. Okay. Type code. This is a thing. And then line number and file name, we're going to see how it's handled by the other function. But these, besides line number and file name, these are our three arguments. So we're going to need to set these up, and then the callback does the thing. All right, so cogen panic overflow. We could just call these panic underscore, I don't know, something like that. Just to reduce left value. Okay, we get the mapping. This loads the thing. I feel like this should be a little function, but whatever. Whatever, we'll clean it up at some point if we want. So we load it into RAX if we don't have it in some register. And then we call pass single argument, which does a bunch of stuff. Like a lot more stuff than I wish it did. Okay. We want to do all this again for, oops, we didn't put an underscore here, for the right value. No, left. For the right value, and you know what? Let's just do this. See, this way it's just a pasta. It's just a pasta right there. Okay, so that's our left value and our right value. We need the type code, which this was an integer argument. here. So we're going to do that. Code gen panic overflow type code. This is not going to be in a register. Wait, why is this? Okay, the thing was wrong. This is in a fucking register. Okay, hold on. See, I thought because it was an integer argument, yeah, this is why it's a good idea to be explicit. This is also oh, wait. I posted from the wrong thing, really. Hold on. Okay, there we go. I posted from the wrong thing. This thing is really what I wanted. The pre-flags, post-flags. Okay. So here, we're just going to say the type code is this thing, assigned to constant, pass single argument, it's probably fine. Right, and then we say we set CodeGen panic sites somehow. All right. And then when we're calling the procedure, rs is this called array? Yeah, so we're using the same name. So rs arithmetic overflow. Now the question is, did I think I did. Yep, that exists. All right, this is one of these changes that has a bunch of moving pieces. OS target does not exist. Okay. Well, there we go. Okay, cool. This is not going to do anything yet because we're not actually calling it ever. Right? So I can go back to here. I can run this. It's fine. So now, let's look at how this is done. Okay. Call array bounds check fail. So we're just going to do this. Okay. So where was it? Oh, I can look for the JNO. Wait, did I delete the JNO? Bin op colon. Oh, our jump was wrong. Oh, because the other one had the J and O and I deleted it. All right. So here, now we're just going to say literally every multiply overflows. And that's going to make us very sad for a little bit, but we're going to make sure this works, etc. Okay, so you make code for procedure call. Cogen panic arithmetic overflow. All right. I just don't like how many fucking parameters. Interp. Wait. Emit code for procedure call. Instruction index. Procedure info null. Callback. Definite flags. Num arguments. Like, that's fucking hard coded, which is banana cakes. That's very error prone. It's fine. So 1, 2, 3, 4, that includes file line 1, 2, 3, 4, 5 here. And then options, I don't know what options, and then hash add end. All right, so this is fine for some definition of fine. These are called cogen panic overflow whatever. Do we literally put debug expression in every bytecode now? Fuck. We need to fix that. It's fine for now. Do I ever use templates or const expert? I almost never use templates and I never use const expert. Like, the thing is, I gave up on C++ around, like C++ 11 was like the last time they added features that I kind of liked. So like I use auto all the time and stuff. But like C++ is a lost cause. There are many, many, many bad decisions made in the language, and a lot of these features just come with a tremendous amount of baggage that is horrible. So I just froze the version of C++ that I use, and I just never change it anymore based on new things that they do. And I chose instead to make a totally different programming language, right? Okay. Overflow left value, overflow right value, and type code. Now, the type code, we're just going to leave it 0 for a second. Actually, let's try something. So this is like, I didn't want to pass a lot of arguments because I wanted the calling of this function to not be that big because we're going to insert it all over the place. So I packed a few things into like this field, right? So the type code, you know, whether it's fatal, whether it's assigned value, and whatever. And I'm just going to lie about it. The operator index, we're going to always say it's minus And we're going to say 16 bits. And once that's working, we can make this encode the actual correct information. All right. Yeah. Oh, yeah. BC, this thing, this giant ugly ass thing. Boom. Boom. Okay. Right. A, B. Okay, that didn't work at all. Oh, because I turned off, we're not using this instruction because when we took the W and checked in, I turned off running that by default. But I should be able to say very debug to turn it back on. Fuck. Oh, maybe I broke very debug. Oh, also, this should break down here. Point break. Okay, this is like when we were compiling Sokoban and we're like, why is it not doing it? What do I think of C23's embed feature? I don't know what that is. I don't care. I literally don't care about anything new in C or C++. I don't. The only reason I'm using C++ for this compiler is to avoid the annoyance of self-hosting with a non-mature programming language. I don't use it because I want to program in C++. So like I literally don't care. If I could do a disrespect speed run versus C++, I absolutely would. Embeds binary data. Yeah, we've been doing that forever. Am I going to rewrite this in Rust? Lawler coaster. Lawler coaster. Okay, so yeah, I don't understand. I presume if we compile this program, we're going to find that we simply don't get here, that we don't generate this instruction, right? Let's see that. Oh, wait a minute. We're not building an x64, guys. This is LLVM backend, which obviously is unaffected because we haven't done that yet. There we go. Okay. Two problems. One, we're not printing anything for the numbers. Two, we're not panicking. Let's make it fatal. Okay, this is let's see if it takes that message. Nope. Weird. Okay. We tried to, at least we're getting here. And then what's, I don't know how we're possibly returning my panic. See, we're like aborting from this function somehow. It's like we're aborting because we're crashing and we're invoking a signal handler, but the signal handler's multiplications are messed up. And so we're ending up back here or something, right? If fatal, we panic. Oh, these aren't going to standard error. This to standard error thing is very verbose. We should figure out a better way to do that. All right. Still doesn't matter. Let's see if the first one looks different. That pipe more doesn't work when it's standard error. Great. Okay, it does end eventually. Oh, guys. Yeah, this has multiplies in it. That's, yeah. This has multiplies in it. So if we fuck up literally every single multiply, this code can't work. Okay, so that's fine though. We're at least calling the function. Let's only do it if size is equal to 1. Let's see if we can get away with that. How do I get the size? The operand type is U2. Oh, it wants me to put the actual number. It's not U2. We try to compute 5 minus 5. That might actually be the right numbers. Oh, but it's not. Okay. We tried to compute whatever minus whatever, and then we want a new line. Okay, and we have left and right. I probably pasta errored in here. Panic overflow. Yep, right here. This is right value, bro. How many times did I go left, right, and it still was wrong? Chew. Toby Chew. Okay. We try to compute 5 minus 17. Remember, this is actually at times, but we're lying right now about the operator. Okay. Okay, let's get the size correct first. So it's just literally the number. So the number is the size here. So we want to say 8, 16, 32, or 64, right? Actually, no, it's this one. 8, 16, 32, or 64. Right? Oh no, that's not this one. It's this one. Let's go back and look. The size is type code and 7. All right. So it's literally the bottom bit here. So I think we just do that, right? You won. What? Wait, we're anding by 7. That's not... That's not going to work at all. Without... So this can be... See, one of the inconsistencies in this language that ends up being confusing sometimes, like we specify sizes in all the primitives and stuff by number of bytes, but then our primitive types are by bits because that was just how you think about it a lot of the time. And like, it just introduces an extra conversion that's annoying, right? So if this is number of bytes, then we multiply that by 8. All right, it's U8. It's probably S8 actually, right? Oh no, it's U8 first. Let's put S8 first. It'll still say U8 because we haven't put the sign bit correctly. So we'll do that part next. So the sign bit is 4000. Okay, so first of all, let's just say U32 code. We're going to do some stuff to it. We're going to assign it down here. Okay. Now if so that's if it's fatal. Okay. And sign bit is this. Okay. And then operator index we'll get in a minute. We're still going to lie about the operator. Okay. Now, signed. Okay. Going to do this. We're going to get a little bit of ASCII spam out of here. We're going to use that. I mean, we might as well do this for A and B. Okay. B. And then so if, right, that's what it was called. Okay, and then fatal. We're going to do this. AOC is equal to, where is this defined? Not there. Arithmetic overflow check fatal. Arithmetic overflow check fatal. We do that. Okay. So now we've got the fatal hopefully correct and the number of the sign and the size all correct. It's S8, 5 minus 17. Okay, great. Now, if I go back here, and I delete this, and now we're doing U8 first. We should say U8. Operand type is U8. Okay, awesome. We've got the right values. Now we just have to say times. All right? See, we're doing this very incrementally. Like, it's so stupid, right? We're lying. We're just always reporting overflow for 8-byte multiplies, but that lets us work on this and make it function. And then we can actually do the overflow detection, right? It's just, this is how you break programs down into tractable pieces. All right. So operator index. If op yeah, so it's just this. You know what? I should add something here. Yeah. Okay. Okay. If op is equal to bin op plus minus times div. Did I do div here? They could be, so operator index 0, I mean, I'm leaving that for error, but that shouldn't really, let's not worry about it. Okay. 5 times 17. There we go. There we go. So now here's what we could do. Is actually jump around that. Interesting. Oh, we're only outputting this for size 1 now again. But I kind of want to do that. So we should no check in this to remove it, but Hmm. So what do we do here? Why is this happening? Okay, so first of all, this comment has the wrong function name. Is it possible the overflow flag is just getting set? I mean, that kind of makes sense. Maybe my JNO is incorrect. Maybe. So what if I do this? Okay. So yeah, our overflow flag is getting set, weirdly, or something. This is fine, though. This is progress. So now we could actually step into that again and see what's going on. Okay, disassembly. We do the IMAL. Wait, why does this say JMP? Did I not recompile this? Okay, JNO. How do we see the flags here? Window, Windows. There's like a no. Debug Windows registers. E flags. Shut up. Just give me a way to put a quarter in the slot. I'm not going to watch ads. Treat me like a fucking adult. Okay, so overflow flag is 11. Bit 11. How many time zones are there in the Soviet Union? What is 10? Because this is bit 10. Direction flag. Okay. Not relevant. Okay, so we do IMAL AX by DX. AX, DX. Whoa! Okay, this has to do with the way that we're doing our 1 byte multiplies. There's trash in the upper part of it. So this just has to do with our 1 byte things not being done yet. So let's do this. So that was legit overflowing, right? Okay, hold on. I'm confused about everything right now. There we go. Do that, do that, do that. Okay. Okay, this is interesting. We theoretically now have overflow detection for all sizes but U8 and S8. All right, so if I go back into our program and I say A S16 is 10,000, B S16 is 8, C is A times B, that should trip. There we go. Arithmetic overflow, we try to compute 10,000 times 8. Oh, okay, this part's wrong. We are tripping. Maybe the move is resetting flag. No, it was like, it was literally that we had trash in the upper part of the register and legit we're overflowing. Like legit. Okay. So let's make that error report correct. Correctamundo. Correctamundo. Now let's refresh our memory once again. Where is the size? The size is the low 3 bits times 8. Now, this already doesn't make sense. See, I was confused at some point when writing this because I sort of have 7 bits reserved down here. When really I only need like 4. But whatever. We're not using all the bits. Here's the thing. If this is going to be times 8, we need this to at least go up to 8. Right? So we'll put F to pay respects. And now we're also, though, so these were S16s, so we should have been putting 2 in the low bits, and we weren't for some reason. So let's go back over to here. And oh, we're multiplying by 8 here. So what we were multiplying out of the range of bits that we were looking at. All right. All right, operand type is S32. No, that's also wrong. Closer, maybe, but also wrong. What? Why am I having such a hard time with this? Okay, size. Oh, because I'm left shifting again. Yeah, no, I know. This is stupid. I've changed my mind like 4 times about what I'm doing, but haven't thought my way through it very carefully. S16, ta-da! Okay, so we can, of course, try this in a couple other cases. This also will not fit into U16, so we could trivially change this. And it's U16. All right, how about U32? What's a good... that's a number, and then B is going to be, I don't know, 300. Yeah. U32, it got that correct. Boom. Okay. Also S32. Okay. How about S64 is going to be 7F000000, right? And times 2. Uh-oh. Did that not work? That didn't work. Okay. Do we not get overflow flag if you overflow into the sign bit on a signed multiply? It fits in 64. It does fit into 64 bits, but it's going to change to a negative number. If I print this down here, we're going to be like, we're going to have some negative number mess here. Wait, no, we don't. What? What is wrong with my brain right now? Oh, dude, we don't have enough digits. I'm used to old computers. Okay, there we go. Array arithmetic overflow. I'm glad people in chat caught it. Yeah, it boggles the mind that this is how many fucking bits you have in a number now. It's astonishing. It's astonishing. Okay, so it's just so many digits, dude. I mean, it's almost 24 digits. And then what would you do? Okay, so this is good. Let's try U64. This will fit. Wait, why doesn't it fit? 7F times 2? That should fit, right? Yeah, because that's the same as left shifting it. What's going on here, people? We have a whole bit left. Why is it telling me overflow here? Right? Look, it fits. Oh, guys, here's what's going on. Here's what's going on. Here is what's going on. We're calling imul every time. Imul is signed multiply. I literally never had to care because we didn't care about the overflow flag. And if you don't care about the overflow flag, the result is the same in these cases. But if you do care about the overflow flag, see, it doesn't know the difference between signed and unsigned multiply right now. Because imul, if we go back to the page, signed multiply. Mul, unsigned multiply. For unsigned, you want carry agate. No, we just run the different instruction. Wait. Oh God, these are all the implicit fucking EAX versions. Oh, that sucks. Maybe we should use a different flag. Because we want to be able to target whatever register we want. How would that work? How would that work? I mean, we could manually detect it, right? If it's unsigned, as opposed to using the overflow flag. That is one option. I don't love that option because, again, we're probably outputting more assembly code. I'm going to start the T water up again. Option number 2 is we bite the bullet and just use the forced registers. We have a way of doing that. I just have to go look up some other code that does it. But we could use the forced registers here. We hate that, but we could do it. Or maybe there's some other flag thing we can do. Testing overflow for unsigned multiplies using imul. This is not. So it seems to set carry flag to the same as the overflow flag always. Oh, wait. No, number of operands is 2. No, it always sets them to the same. So there's no way of using carry flag to differentiate relative to overflow flag. Would I make a SQL for braid? I don't know what I would do in a SQL. All right, tea, water. We're doing another golden monkey, everybody. Okay. How does Kik have $100 million? Who is sponsoring that? Why don't they pay me $100 million? I mean, I'm basically gambling right here. Yeah, I don't know. What would I do with $100 million? Well, I would certainly start an operating system project. Aside from that, I don't know. Buy some tea. Why do I need 100 mil for that? I don't, but I need probably at least a spare 20 million for that to do it seriously. Unix based? No. No. Guys, Unix is from before I was born, and I'm older than all you guys. Not you. Well, there's probably some exceptions. Yes, when we have this many people in chat, there's probably a few people who predate me. Unix wasn't even good design when it was made. I mean, there were certainly a lot of arguments about it at the time. I think it had a place. It certainly had a place. But I don't think most of the design decisions behind Unix are appropriate in the year 2023. I think they're mostly no longer correct. That shouldn't surprise anyone. Computers have changed tremendously in 50 years. Why are you running the same operating system? Like, it doesn't make sense. Okay. So what do I do? Let's see. I don't think we have this problem for add, although we might. Let's try it. Let's try it with add. Okay. So with add, we're fine. So this is literally just a multiply problem. For unsigned multiplies, I could use the lame-ass multiply. Which, by the way, if we use the lame-ass multiply, we could also do that for imul, because we have lame-ass 8-bit imul. And then we could just use the... So we're down to two options. One, use lame-ass mul. Two, detect overflow manually like we do in the C++ code for unsigned and 8-bit multiplies. Now for unsigned multiplies, let's refresh our memory. Unsigned multiplies right here. So for 64, for smaller ones, we can basically extend and check against a constant, right? And for 64 times 64, we need to look at the upper word, which is a thing that we have. The mul instruction gives us that anyway. So this is not really particularly hard to do it this way. But it's still more code because we have to output code that like loads this into a constant, and you know, because this code is dumb, if you do a bunch of multiplies, which you probably do, we're going to load the constant a bunch of times. It's going to bloat the code to turn this option on if we do it that way. We don't really want to do that. We want the code to be as unimpacted as possible by this check. Now that said, it's easier said than done. Like, it does have an impact. What's the difference between lame-ass IMUL and normal one? Lame-ass IMUL does not let you select the target, the source, or target registers, really. You get one choice of what register, and then it's times EAX and putting it in D:A, right? So the problem with that is we have to, like, you know, spill A and D if they're in use and whatever. But we can do these things. All the calls to the panic routines are the big bloat. Yeah, I mean, that's the other reason why I might not worry about it, is because by the time you put the function call in there, like, maybe that's super bad. Now, that said, we could, I think you did a thing for returns where we have one return point that you jump to, right? We could do that for these as well. Although, like, you still need to go there with different arguments, and maybe by the time you do that, it doesn't really save anything. But, and that's also more complicated and more than I want to do right now. Okay, I've got another golden monkey. Monkey! Could just jump to a bunch of specialized routines on cold pages. Yeah, I think we should consider doing that. I mean, right now we have a thing where you could set it to be fatal or not. So it might return, but I'm not actually sure how useful that is, because, like, well, I don't know. You can imagine you're putting a server into production and you want it, and you're pretty sure that there aren't going to be overflows, but if there are, you want them to be non-fatal and logged. So maybe it is useful, but you know, like, if you have some loop and you're doing an overflow in there and it's non-fatal, you're just going to get spammed by output. Anyway, though, do I do lame-ass? My inclination right now is to do lame-ass mulls for all of these. So here, let's sketch out what this looks like. So if we're going to say Okay, if okay, here's what we're going to do. For the moment, we're going to say we're going to do different stuff based on what's going on. So if signed, if size is equal to 1, else, all right, else, all right. So if size is not equal to 1, we're fine. If size is equal to 1, because we don't have good overflow checking, we're always going to jump around, all right? Jump around, jump up, and jump around. Okay, otherwise, we always jump. So now we're going to output this. So we've got no checking for unsigned. Oh, but this isn't what it would look like. Right. This is what it would look like if we do the manual checking. If we're going to use the actual lame-ass mul instruction, we actually have to go replace this. Which obviously, or I kind of don't want to do. Are lame-ass muls faster? I doubt it. I mean, this isn't really going to give us... What's a recent CPU? What's the... What's the website that has all this? I'm not thinking of... okay. Dude, there's so much shit now. All right. Mul and imul are... They're all listed as 332, except for this one. Wait, no, they are different speeds. Hold on. Dude, they're like all different speeds. Lol. But ops latency. I mean, dude, multiplies are so fast now. I'm looking at an old AMD. Oh. Yeah. Oh, K7. Yeah, good point. Are the new stuff down at the... I just need a better site. What's the site where you actually pick it from the drop down? uops.info. All right. Table. What's your job? Open Table. That's the name of a startup in Miami. Okay. Instruction. Mul. Okay. There's just so much crap in these things, guys. Is Alder Lake new? That's maybe the new one. I don't know all the lakes. This seems like it's kind of going in order. Okay. imul. How do I read this? 3:9. I don't know how to read this. What does 1 arrow 2 mean? I need an education about how this works. throughput one. Mul. It's I don't know how to read this. I don't know if I care enough to figure it out. I mean, the couple that we're using a few, we're using like R16, R16, R32, R32. Oh, these just say 3. Okay, this must be, well, I don't know. I know how to read the 3. That's fine. So these are 3s, basically. And then this is also 3. Yeah, it's like fine. Variable latency due to memory access. Yeah, it just seems like some of these with the brackets are not memory ones, like this one. This is the implicit A register one. I don't know what 0 means. Look at all the, dude, just to do multiplies. To support all these different forms of this instruction. Imagine how much crap is in this chip just for this. And then multiply that by everything. Risk V when, I mean, we'll do it at some point, but like, all right. Anyway, so we still have our fundamental decision. Do I do it manually? And I think the answer is yes. For now, I do it manually. Although, yeah, I have to do it manually. We have no 8-bit IML, so we need to check manually for overflow. Let's just do this one, and we'll see, right? So signed multiplication overflow is, we're going to have to do all this shit in LLVM as well. God damn it, dude. That's going to be hell. That's going to be hell. All right. Oh shit, this is wrong. Lol. Okay, good thing we saw that randomly. This is for checking checking the bytecodes match. That used to be right And then I changed the instruction. Oh, that could have been bad. All right. So I was looking for this. I'm in the wrong file. We're looking back here. And when we do times signed, oh, by the way, this is like, this is like only for mul. All right. Bin op times. Why not cast a 16-bit? Because even if we do, like, we could mask the trash off. We do cast a 16-bit, sort of. We could mask the trash off, but then we won't get a correct overflow anyway. Like, we have to manually check this case or use the lame-ass IML. Those are our only two options. I'm a traveling rat. No, I'm at home today. I just got up. It was 7 in the morning. When I started streaming, I didn't feel like being on camera. Now it's several hours later. Okay. So, okay, let's go back here. For 8-bit signed, what did we do here? We say, oh, we actually do it in S16. Oh, right. This is actually how we're, okay. This changes things a little bit. I think it's maybe fine. But we have to mask the trash off. I think. No, maybe we don't. Maybe we don't. Because that's just going to overflow no matter what. So I don't think we have to mask the trash off. Okay. So we need to know what is P? Right. So we want to compare. We want to do a 1-byte compare. We want to do a 1-byte compare on compare versus immediate on A to determine a 2-byte compare. All right, do we have that? compare. How do I not have compares? I guess we don't really use compares that much. We just jump based on what's going on. Overflow will literally be encoded in the upper half. No, I mean for this. Okay, for this. Yes. I mean we can do that version of it. It's just okay, there's two ways of doing it. There's two ways of doing it. I want to figure out, so basically you could just look at the top half and say, is it -1 or 0? And, you know, were the inputs -1 or 0? Like, that's a lot of instructions. That said, this is an 8-byte mul. How often do people do an 8-byte mul? Not very often. So maybe it's fine. But it's complicated and it's maybe annoying to get right. So if I just do a 2-byte compare, I'm just going to write something. Compare 16 that doesn't exist right now. Compare 16 immediate. A versus -127. The thing is, we want to do two compares and do an OR, right? And I don't remember the good way to do that. Sorry, -128, 127. Or, we must have an OR, right? Or, there's like the thing where you move, it's like set CC. This is the thing where you put it into the register, right? So we would do like set CC. I forgot this part, by the way. This is such a bunch of crap, dude. Set CC less wait, temp 1 and like I need to get temporary registers. Yeah, I don't know. I guess we don't use the other ones, so it's fine. Temp 2. But since this is an OR, I could do the OR by doing like an add with carry into my single. I don't know. We're just going to do this super stupid. And then, okay, so this OR, this is the size. And then does OR set condition flags? There are 637 matches for the string OR, obviously. OR. Flags affected. SF, ZF, and PF are set according to the result. So 0 flag we could use. So we OR it, and we say J and Z. It's like JZ, but different. Do we have that? I mean, we have... I mean, I probably shouldn't keep making these. I should probably use this. But we're going to be lame and go. We're way out on the limb of how many random ass things we're doing right now. So we're just going to do this. J and Z. J and Z instruction. Yeah, it's all on the JCC page. J and Z 7.5. Let's just make sure that's 8.5 for these. Not supported in 64-bit mode. What? What? Dude, why? How is Babby formed? A minus B greater than C does a two-ended compare. Right. We actually do use that in some cases. In fact, we use that for array bounds check. So if we look here, for signed indices, just do an unsigned compare, which will catch the case of being too low and too high. But that's only when one of them's 0, maybe. Okay, anyway, we'll figure that out later. I just want to get this working. So we set CC. This is like really not great. Okay. So JNZ32, let's go back here, is 8.5. And we'll step through the code and verify that that's correct. Let's go here. We want our S8 to be the first thing because that is what we're doing here with this giant disaster. Now, do you see? So when systems are simple and straightforward and elegant and support things thoroughly, it's really nice. We're doing all this crap because there's singularities in like the instruction support, right? If we did nothing else, if we just took the x86 processor and just made a new instruction set for it that was 64-bit, but like actually fucking designed according to what people want to do, and we didn't worry about backward compatibility of all these old lame-ass versions of everything, it would be so much better, right? And Intel talked about doing that lately, finally. But I don't know if they're going to do it. Like Itanium or the... Yeah, I mean, dude, that's a very mid argument, and you should know that. There are times when things don't work, and times when they do work, and sometimes when things don't work, especially if it's on a massive, massive project with many fucking people involved, you can't even pin down the reason for the failure, right? Sometimes things are good ideas and there are 17 implementations of them and 16 fail and only the 17th succeeds. Very mid argument. You were part of that argument. Well, okay, I understand if you had personal skin in the game. What is Intel removing? I forget. Basically, they did a press release or something. They floated the idea of releasing a new instruction set just for the current CPU, right? Which I think they should have done when they went to 64-bit. But yeah, we've kind of been suffering from the fact that they didn't. Am I talking about removing the IA16 real mode? No, I'm talking about everything. Like, look, when you're using this AMD 64 encoding, which is what we're using here, every single 64-bit instruction, in addition to being kind of big because you want to specify bigger constants and bigger registers and stuff, has an extra byte in front. Like literally every instruction has an extra byte in front saying this is a 64-bit instruction. So your code is like just that, like sucks. It uses up a bunch of instruction cache, right? I mean, that's far from the biggest problem, but it's just one example, right? There's all the like the hacks about, you know, we clear out the top 32 bits to 0 when you do a 32-bit op. There's all the weird instructions, right? Yeah. No, but I think the reason they're talking about doing it is because it's quite often these days when the actual instruction decoding becomes a bottleneck. Like, I don't think it's a bottleneck for the vast majority of code, again, because most code is just waiting on memory anyway, right? But like, I don't know. I don't know that much about CPUs. I just heard these things from people. Like, when you actually have performant code, the instruction decoding can become the bottleneck. Intel doesn't want to carry this complexity along forever. I agree, but like the thing is, it's the same with Windows actually, right? So both Intel and Microsoft have benefited a lot from being very, very good at backward compatibility and providing that for people over a very long time, right? That's obviously been a successful move for both parties. However, That is part of an equation, right? And the output of the equation changes over time. It is something like, how many resources are being expended to give you backward compatibility, for example, on the chip from moment to moment. How many limitations are being put into place when we work on the chip? How hard is it to deal with all this stuff, right? How much of our time do we spend dealing with it? And then there's the benefit side of the equation, which is, how much do we benefit from providing this backward compatibility? And both of those shift over time, right? So as the complexity goes up, because you just kept adding things and things and things and things, and they're not even consistent with each other and all this, the cost side of the equation goes up. And this is not necessarily following from that, but it happens to be true in our current reality. The benefit side has gone down because, and this is sad, I don't like this, but like there's way fewer people who like make things that output machine code now than in the old days, right? So like putting out a new architecture, like a whole new thing saying, hey, everybody output this. It's not that hard to get traction on that because there are fewer parties involved. Also, Apple sort of proved that you could just translate it anyway for people who are using the old thing, and it's fine. They did a great job on that. But also, I don't know. Like the percentage of programmers who even interact with anything like this is just really low now, right? So both sides of those equations are changing over time, or both of those major factors in the equation, both the cost and the benefit, are changing. And so at some point you would expect there to be an inflection point where the correct decision changes, right? That's just what you would expect. And so that's why I was saying the other thing is not a very good argument for this, because something that happened 10 years ago or 20 years ago, like I said, first of all, usually it's very hard to know what's right anyway, even if things succeed or even if they fail. But something that happened 10 or 20 years ago was at a different point in this cost benefit equation, right? And we're in a different place now. Anyway, I think that would be what I would do. Like Apple showed clearly that you could just switch your CPU out and translate the binary and nobody cares really, right? Like so many of these M1, M2 Macs are just running x86 code right now. Most of the time. So yeah, just do that. I mean, if they can do it, you can do. It's the exact same thing. Except if you design a newer, sleeker instruction set, it should be an easier job. Okay, let's go back to this fucking pain here. Oh, the pain. Oh, the pain. Intel arguably couldn't afford even that much cost. I don't think that's true. I don't think that's true. Again, everybody's program is like 10,000 times slower than it should be. And nobody cares. All right? If people actually cared about performance to that degree, well, the people who do care about performance can just compile to the new Arch, right? And then everybody else, like, nobody fucking gives a shit. But my understanding is it's not an emulator, right? I mean, well, there's probably some stuff you have to emulate, but what you do is just binary to binary translation, and then you just run your native code most of the time, right? That's like the only way to do it at reasonable speed. It's not like it's a bytecode interpreter that runs x86. Yeah, I don't know. If I were Intel, I would do it, but I'm not Intel. Okay. So I need to call pick temporary register. And I need to pass it exclusions. Let's see. Yeah. Could I just do this twice? You know, I could just do 2 jumps. Yeah, this thing does it twice. All right. Okay, so this is really a disaster. So compare 16 immediate we don't have. We have add immediate. Compare 16 immediate. Let's call it immediate 8. Just okay. Okay, so let's go, whoops. Let's go to index, CMP, RM16, R16, 39/R. So we need the 16-bit, op 16-bit, 39, and then wait, immediate. I want this one. 83/7. I don't know what /7 means. I'm going to hope it's it's this. Hopefully. We're going to see what code that generates because we don't trust that at all. I trust that as far as I can throw it. Because it's just bits, I cannot throw it very far. Signed is a keyword, by the way. In case you didn't know that. Or does not take 3 arguments. Ah. Okay, let's have an entertaining time now. Oh, our breakpoint's in the wrong place. We didn't hit an invalid instruction. All right, stepping in. Do them all. Disassembly. Okay, so we're doing AXDX, 16-bit mul. We've got some E flags going on. Wait. The fuck? Why didn't we do our special thing? We were pressing down the special key to play a little melody. For some reason, did I recompile the compiler? Yes. So see here we've got a JNO, which is, you know, maybe that, but we're not doing any of this stuff. The question is why? Why? Okay, so it's going to be line 5. Let's just break here. BC debug. So you open the window and start typing, and it misses keystrokes, by the way. It's the new innovation in Visual Studio technology. Are we running the right program? Hold on. Did I literally just look at this? Yeah. Okay. Okay. We literally never get there. Oh, because we didn't put very debug here. All right. Was I not doing it here? No, I was. Okay, so for some reason that's not throwing, but this is throwing. Yeah, so we only initialize that in one. Okay. Let's just do this. It's not going to fix this problem. Okay, we get here. Is it signed? Is size 1? No. Why is size 8? Okay, this might not be the same spot. Yeah. The problem is there's a lot of files with a multiply on line 5. There's a 1. Whoa. It's a 1, but the op is not times. Oh, it is. Why didn't we go here then? Oh, it's not signed. Okay, here's one. Okay, we're going to this code, temp1, temp2, temp1, temp2, or... So we are generating this. Debug expression, load info index, interp, load info, no active loads. This is going to be the right file. Actually, we know 2 is the target file. So it looks like we're generating that code now. Maybe let's give it another chance. So if I run this and step in to the multiply and we look at the disassembly. Okay. This is better, for some definition of better. We're generating the wrong shit here. Okay. Starting here. So our compare is just wrong. It is a 16-byte compare, but this is not with an immediate. This is not with an immediate. I thought it would be the same as add. See, I only do this like every 2 fucking years, so I have to refigure it out every time. So add immediate 16 81/0. IW 81/7. Now the problem here is we're only putting in 1 byte. This is what I don't understand. Oh, we're putting in 4 here. Dude, I don't get it. Yeah. I could sign extended and just use this, but this is literally exactly the same. I mean, well, not exact. It's just prefixes. All right, so I'm going to try. It looks like I'm supposed to do this. Let's call this constant. Okay. This probably still isn't right. I mean, it sure seemed like it wasn't, because it was dereferencing. It was an indirect, not an immediate. Right? As we say. Yeah, see, we're doing an indirect. So that's really confusing me. And now we've just got more bytes of trash out here. I mean, dude, we could just zero them, because I literally don't care at all. We could zero them and do our 60. Yeah, you know what? Fuck it. We can bring this back if we want it to work. We just want, okay. 0 each of these. Okay, and then, dude, I don't like this. Compare 64 with constant U8. Fuck, except it's an S8. Dude, I don't know. Let's just get instructions. Fucking 225. Yeah, of course. Of course, because it's C++. Well, I mean, it ran. What does that mean? What is that? Oops. No. Let's go back in. Disassembly. Okay. IML. We store the result. We clear these. We compare RCX with that BL. We do the OR. It sure looks like it. Okay, let's see. Let's do the time warp. A S8 equals minus 100. B S8 equals 2. This didn't detect overflow. That may be because we're comparing against UA, although it looked like it wasn't. Okay, let's go there. Let's go to here. Boom. Okay, disassembly. CLDL. CL. DL. 156. What? Oh, minus 100. Okay. IML. DX. AX. Okay, it's... See, we're not fucking sign extending. See this? It's got trash in the top. It doesn't know it's a negative number. I was trying to avoid having to do this, but yeah, okay. In our IML, remember how we do this shit? How do I sign extend? This is just, guys, it's been like 2 hours. All we've been trying to do for 2 hours is deal with the fact that this instruction set has a hole in it. This is like, again, this is the importance of this shit. Let's just do this. We don't need 64. Okay. Anyway. Okay, it's still giving us a positive number. Let's see. Let's not break there. We want this. Okay. AL, DL. So we have AX. Okay, that's sign extended. We have DX. Okay. So this is right. We do an IML. FF38, which is, I don't know. I mean, what's, it should be minus 200 in hex, right? Yeah. So we have minus 200. That is, however, less than minus 127. So that's the part that must not be working. Okay, we're storing that result. I don't know what's happening here. What the actual... This is the printf. We just didn't do the check. Like what? There's just no check. What happened? What is it? Why are all these windows up? Stop. It's so annoying, dude. We should have done the check. Okay, let's look. Line 35. Let's put it one down. 35. No ABC. Oh, shit. Oh, I have no AOC on here. Lol. Okay, thanks. Still not right, but we can at least look at the code now. Okay. Once again, disassembly. IML. Okay, so we've got our FF38 again. That's fine. We're comparing the wrong register. We're comparing C. But our targets are A. Wait, no, they're C and D. Okay, wait. IML always puts the result in D:A, right? Right? Mul does, IML does not. No, mul, it's that those are source operands. Yeah, no, you don't pick outputs for this. It always puts them in D:A, right? Hold on. Destination is multiplied by the source in the destination. Oh. Wait, what? Okay, anyway. So we do IML AX DX. So we should have right, it's fine. We have the result in AX. But we're comparing our CX for some reason. Why are we doing that? IML works like every other x86. I'm just confused about the 64-bit IML. Where does the top half go for this one? Do you just not get it? Or, I mean, like this one. Anyway. IML has no top half. No, it does though, because it says twice the size of the intermediate product, twice the size of the input operand is truncated and stored. So I think like the way that I read that is if you do the IML R16, it'll put 32 bits there. I don't know, dude. Anyway, it doesn't matter for what we're doing here. It doesn't matter for what we're doing here. We just need to figure out why are we comparing. See, we're supposedly doing the IML with A. Dude, I don't know how the exclusions and stuff works. Maybe Ryan can help me with this. Like, I don't know if that's the problem. Like, we're calling print, this A is like our value number that gets mapped to a register, right? Print math bin up does some stuff with that. That outputs the IML. We're trying to use it again down here. And we're getting a different register. But that shouldn't really be possible because we're not using, so this pick temporary registers is giving us, it's giving us B and SI, right? So it's not like we could have overwritten it. But we're comparing RCX. Maybe just our instruction generation is wrong somehow. I think when the register allocator is off, it will realloc every time they aren't sticky. So how do I say reuse the same register that we just used in that IML? Right, so in print math bin op, it's funny that it's still called print. We just call, oh, this is the float version. These are just the value numbers, P0 and P2, right? Those are in this array. I mean, I guess there's this vreg prepare, but probably have to pass it back out of the print function. But I don't, like my API for any of these instructions doesn't take x64 registers, right? Like I want to just be able to pass the value number in and say it's still the same. Okay. It's such a butt pain that these multiply instructions are also weird. I guess these days, if you want good multiply, you use like AVX or something. I wish we could just clean all this up, dude. Wait, compare 64 with constant is taking a physical register? That's my problem then. My problem is I'm confused about that. Oh, you're right. When I wrote these, yeah, okay. See, this is why I should have stopped using int for all these a long time ago. There should at least be a type def that says machine ass register, because then I wouldn't have been confused. But I'm confused because I was using int for value numbers for a long time, and I'm also using them here. Okay, that's my problem. Is I'm passing the fucking thing. So don't you have like a get mapping? So I could do this. Okay. That's what, if I worked in this code more often, it probably is less likely that I would be confused about this, but yeah, I still get confused. Operands. Wait, is it just A? Yeah, it's just A. All right. Hey guys. Except no, now it's failing on 5 times 17. All right. But let's look at that. Let's look at that. One of these days we'll get it right. This is just such a pain in, dude, if they just gave us a mull, we would be fine. We would 2, 3 hours, 5 hours ago, we would have been happy. Okay, CLDL. IMUL. Let's take it off hex for a bit. CL, 5 times 17, great. IMUL. AX, DX, okay. We clear out B and S. This is a bunch of BS. Why are we comparing R15? Why is this R15 now? God damn it. Okay, it's still wrong. I need to use the P array from vreg prepare. Oh, does vreg prepare overwrite? Overwrite the P? So, okay, that's confusing. So it starts as an array of value numbers, and this maps it to machine registers. I'm just going to add, this is stupid. I'm just going to add another fucking thing. Okay. Of course, we're C++, so we have to tell it redundantly in the header file. So I don't do this. I say why was I saying A also? That was like frickin' wrong as well. Anyway, gonna do this. Dude, this is so hateful that we have to do all, like, they just didn't want to give us a multiply that we wanted. Print math bin op does not take. Okay, we'll do that. Okay, still doesn't work. What did I get wrong? Dude, I am ready to throw the computer out the fucking window at this point. I hate this. This is like literally everything that I hate about programming. This is all completely fucking stupid. All right, so we IML 5. We get the right answer, 85. Great. We're comparing RAX with minus. Okay, so maybe we're not doing a signed compare or whatever. Is set L, is that an unsigned compare? I don't remember how any of this works. Let's see. BL. 0. Okay, so we're not less than that. Zero. Oh, our jump is wrong. Lol, we want a JEQ. That's a relatively benign problem. JEQ relative. Dude, motherfucker. Oh, we do have it. I just can't type. All right. Hey, this is good. We wanted this to go off because this is our legit. We finally, after however many hours, we finally got 8-bit multiply overflow detection. Oh my God. All right. Let's try this out. What if it's 100 times 2? That should also overflow. Because it don't fit. You can't do, we could do 50 times 2 though. Hey! Do 50 times minus 2. Uh-oh, that's wrong. That's wrong, guys. We almost have it. We almost have it. Okay. Why is 50 times minus 2? Is it offensive? Did we culturally appropriate that minus 2 is an important number in someone's culture? Okay. Okay, great. We have minus 100, aka 65436. BL is 0. Okay, so this compares set G. Yeah. Set G is only for top Gs who do not acknowledge negative numbers, right? So like G is I think unsigned, but there's like above is signed or something. Does anyone who actually knows what's going on here want to verify this? I think I want set A. But you shouldn't, like, look, if you make an API like this, don't have things like above or greater to mean, just say signed greater or unsigned greater or whatever it actually is. You know what I'm saying? Set G should work for signed. I don't know. I'm guessing this is the problem because I've had this problem before. Let's just see. See how we have both of them defined? It's because we have to use them. Let's see who uses these. Above. That was us right there. Above, below. What are we doing here? Memcomp. Okay, we don't really use it. Maybe that's a bad sign. Maybe that means it's the wrong one. It didn't help. Okay, change it back. Online documentation. I mean, the online documentation is just a copy of the Intel documentation, right? So it is what it is. I kind of need to go get lunch or something, but I don't want to give up until this is done. I mean, it's pretty clear though. Like, look, we do the IML. We got a 1 in SIL because RAX is being considered greater than 7F. So this is what's confusing to me. Is it that we're doing an unsigned compare somehow? I thought compare is the same for signed and unsigned, and it's just the flags, right? But the result of this is we're accidentally doing an unsigned compare for some reason. IML clears upper 32 bits. Yeah, but we're, oh, right. I thought we were doing a 16-bit compare, but we're clearly not. This is a frickin' 64-bit compare. Right, because I mean, we could re-extend this, or we could make the compare 16 work. I'd rather make the compare 16 work, but that seemed annoying. But since everything else basically works, yeah. So the point is, this actually is not a negative number because that's all 0, right? Now, if we were doing a 16-bit compare, it would be a negative number. All right? So we could go back here and say, like, why is this wrong? So we're saying 3.9 for 16-bit. 8.3. This opcode extension and mod RM are the same thing. And then 2-byte constant. But this is giving us an indirect, so maybe I read the table wrong. I don't know. We want to compare register 16 with immediate 16. Oh, this is 8.1. Well, we could do this one, 8.3/7 byte, right? That's what we did. Except I did change it. I changed it back. But this is, the 8.3 means 1 byte, and that's what we want. I guess the /7 is the wrong part. Yeah, opcode extension just calls mod RM on the same arguments. They're like aliases for each other. Okay, so let's do this. So this is still going to be wrong because there's no reason why it would magically be right now. In fact, yeah, so it's turning into an indirection again, which I don't this must be the /7 is wrong, right? So again, if we look at the disassembly, like what the fuck is that? And then there's a return. It's not just that it's an indirection. It's laughing at me. Guys, it's laughing at me. Why not IMAL and then sign extend? I mean, dude, whatever. We could do it so many ways. It's just like, yeah, we could try doing it a different fucking way. We're lost in the maze of ways. Yes, there's all sorts of ways of doing this. We're just trying to get one of them to work. Just trying to get one of them to work. If we, for some reason, can't do this one, we could switch to another one, but we'll have problems with that one too. Like, that's the thing. Don't laugh. The mouth on the thing doesn't move. It looks fake. Like, I could just type a Twitch chat saying, why don't you just compare it against immediates for 8-bit? Like, yeah, why don't I just do that? Because it's not working. That's why not, right? Like, this is not the right way to say /7 for whatever reason. I thought 3 meant register and not memory. So that's my only guess about why this is wrong, is that this is not how /7 works. But then I feel like it is, because for this one, we're doing the same thing. And we're going 8.3. We're going rex w. We're doing this one. rex w 8.3/7 ib. So I don't know why that works. And this doesn't. Except maybe it's like literally the same. Like I don't know what you want from me. This is actually wrong, but it doesn't matter. Wait, why did I put a 3.9? Guys. I think my brain is out of brain juice. The reason I didn't spot that in the disassembly is that's a different compare. So the 3.9 started one of the different compares, and then that's how it ended up in indirect. Okay, well, hold on. Okay. Still wrong. Wait. Build, run. It appears to run. Hold on, that's the compiler. No. What is happening? What are all these windows? Stop. Why is this real small all of a sudden? All right. Hold on. Just for avoidance of doubt, make sure we compile it here with the right options. Here. Do them all. Disassembly. Set L, set G, or. Hey, look, we're comparing. Oh my God, it actually is correct looking. All right. So, if we go minus 50 down here, that's fine. Minus, or 60 times minus 2 is minus 120, which is also legal. But it is, as we say, how about 64 times minus 2? That is, as we say, barely legal. This here is your barely legal programming stream. $65 is not legal. All right, we finally got it, everybody. I am exhausted after all that. Oh my God. Okay. By the way, we're not done. Like, we still haven't done unsigned anything. We're not checking unsigned at all. We're going to have tests after we finish implementing this on all the backends. We're going to have tests that are literally all the sizes times signed or unsigned times all the operators. It's going to be an annoying number of tests. No more laugh. I know. I know. Okay. I will love it too. I don't love it because this Windows 1, 2, 3 bullshit, depending on where things are in the taskbar, is not very good. If these guys had ever played an RTS in their life, they would know you should just be able to hit Control 1, 2, 3, whatever on any program to assign that group, and then Windows 1, 2, 3, and whatever. And then you could dynamically do it all you want. But they've never played fucking Command and Conquer, so they don't understand UIs. Do I plan on moving away from LVM? Well, we're working on the x64 backend right now. Like, we've had our own backend the whole time. It just doesn't optimize. But a lot of we do a significant number of so-called optimizations before the backend anyway. Just not enough to actually consider it optimized code. They were granny shifting instead of double clutching. I know, man. Dude. Don't granny shift when you should double clutch. You never had me. You never even had your car. All right. Are there certain game UIs that would teach us how to build better app UIs? Yeah, like all of them. Like UI people on like web and desktop apps think it's like challenging to figure out how much space to put between the lines. All right. That's like their idea of fucking rocket science. And they release entire updates where the lines have more space between them now. And it's like, dude, video games they think so much more multidimensionally about all that stuff. It's like, it's so absurd. It's just what happens when you make all these jobs and they're very stratified so that the responsibilities are so small. You just expand them so that you think those responsibilities are big, right? HTML, CSS makes it very hard to space lines properly. That is true. No lie detected. All right, we're going to take a break here. I think we're going to take the W, though. So we're going to have to run all the tests to figure this out. We've already worked about 5 hours today. It's a little afternoon, and that's basically 5 work days for a programmer at Facebook. So what do you want? Okay, let's run the compilerino on the testerinos. Okay, so when we come back, we could do unsigned. And then maybe build out the test a little more. Because we want tests that fail. Like this test right here that we made is just testing that we don't fail on things that don't overflow. But we want to test that we do correctly detect overflow for all these types. And then once that works, we could test that on x64 and bytecode execution. And then all that remains is the horror of LLVM, which we could get a start on today and maybe finish. Show as little on the screen as possible. Yeah, dude, it's a disease. I don't know why these people think they're learning something when, yeah, the principle is show as little on the screen as possible. Also, I mean, this extends to shit like, I mean, they changed it back finally, kind of. But remember when all the icons were monochrome and like all the texts were uppercase? Because they decided that was better and it was like unreadable and you couldn't tell the icons from each other. Hey, they spent a lot of programmer years making all the icons monochrome. And now they've spent a lot of programmer years adding color back. It's like, it's so foolish. I don't know. I don't understand how it gets that bad. All right. We're going to make sure that this works. Hey, all right, so we're going to take that W. Thanks for hanging out, everybody. We'll probably stream again today. I'm having a good time doing it. Adding bounds checks to x64 incomplete. Let's make sure there's no... I could have broken something. Nope. Doing great. All right, thanks everybody. We'll stream again later on. Have a good time in the world. Have a party, be a party. We'll be back later. See ya.